right? So the first note is exam number 2 was scheduled on next Monday, I believe. Uh, but I feel that might be a little bit rushed. I would like to give you more time to review the topics we have right now. So I'm just thinking about it, perhaps postpone it by 2 days or by 1 week. So make sure you check your announcements. And I believe I'm gonna make my final decision no later than this Wednesday. Uh,
So actually,
mhm.
I had no idea that was going on, but I thought we were supposed to have like a quiz or something. So would 1 week be more appropriate, and then have like a quiz in between or something like that?
Okay, yeah, definitely. Actually, I prefer 1 week as well. Hopefully, I prefer to give you an additional weekend for you to review everything. So that's actually my thought as well.
Awesome. Okay, that makes a lot of sense. Are we gonna
Hmm.
have like you mentioned a quiz like last week, but are we
Yep.
gonna have a quiz for it or no?
Yes.
Like practice.
Yep. Perhaps, gosh, I had a really busy week last week, so I
No,
haven't
it's
been
totally
able to do
understandable.
anything. But I think I'm gonna directly copy one exam from last semester as a quiz. Then you get a feeling of what you should expect.
Okay,
I'm gonna post the quiz perhaps later today, right after this lecture.
perfect.
All right. So I think last lecture we talked about a lot of math, how to solve ODE, like homogeneous particular solution. That might be really confusing, especially I didn't make any notes to the actual slides. If you check the notes, you are going to see 4 or 3 slides of equations. So here I would like to emphasize how to use these equations. Okay. In this class, you don't have to know how to solve ODE during the exam, but you just need to know the key outcomes. All right. So in lecture 8, we talk about a system which is mass, spring, damper. And then this system is subject to a dynamic force. And then this force has a given amplitude and is a cosine wave with no phase lag. And then we want to measure what is the corresponding displacement, xc. All right, so that's the system we have. If you want to describe the system using a ODE, mx double dot plus cx dot plus kx equals to f naught cosine omega t. So that's our original ODE. So on the left-hand side is a very typical spring mass damper system, but on the right-hand side, we have a harmonic excitation, and it's a cosine wave, okay? So to simplify our discussion, we just normalized both sides by m. In this case, then we have 2 omega n zeta x dot plus omega n squared x equals to f naught cosine omega t. One thing you have to pay attention that is in these formats, your force amplitude is no longer big F naught. It actually becomes small f naught, which is f naught divided by m. So that means your f naught has actually have a unit of Newton per kilogram, right? Then we discussed about these standard format of force harmonically excited second order system. So what we have is we know that our solution is xt because it's a inhomogeneous ODE. Then we have 2 parts. We call the first part homogeneous solution, or in your in this class we call it transient. And then the second one we call it a particular solution or steady state. So in my previous lectures, I emphasized connecting the original system equation, your standard mathematical equation, and also the figures. So let me draw the figure here. So in the X domain, we have time. And then in the Y domain, we have, in the Y axis, we have the solution XT. As we know that if you check my MATLAB code, you're going to see your response will be something like this. All right, that's 0. So if you look at a transition, if you look at the time domain response, you're going to find out there is a certain point. Let's name this as TTR. I call this transformation time. So after this TTR, you're going to see only a single sinusoidal wave. So once you see your time domain response gives you a single sinusoidal wave, then we call these steady state. So this usually happens when time is large enough or time approaches infinity. So, but how this TTR look like, that all depends on your system. For most of the system, like your car, the transient state usually dies out very quickly. If you hit a bumper, then the transient state usually dies out within seconds. But then for some like low speed or really flexible systems, these might keep vibrating for days. So there's no like a cutting, like a rigid lines. I should say that there's no rigid time point. I can confidently say that it's already steady state. The only way you check it is you just check the time domain plot, and then to see if a single sinusoidal wave appears or not. If it's still very noisy and still oscillating in more than one frequency, then we don't think it's a transient state. But we don't think it's steady state, it's still transient. So if you see some crazy vibration, like a vibration more than a sinusoidal wave, then this location is called a transient state. All right. So how does these solutions look like? So we have X, H, which is our transient. We also have our particular solution. So your transient state or your X edge, it depends on, you get this format from free vibration. So the mathematical expression for your transient state is determined by your free vibration. So in our case, we actually have 3 different formats: zeta smaller than 1, underdamped, critically damped, or overdamped. So in the class, to simplify our discussion, we ignore the last 2 cases. But then if you check my MATLAB code, I actually provide the solutions in MATLAB. Make sure you check it out and understand what's the difference between these, each of them. And then for the first case, we know that your response should be amplitude times minus zeta omega n t psi omega d t plus phi. So you already learned these from free vibration. So your zeta, omega n, omega d, they are all system parameters. So that means if you know your M, C, and K, you can easily calculate these zeta, omega n, omega d from the free vibration lectures. And then the things to be determined, they are A and phi. They are related to your initial condition. But one thing you have to pay attention, in free vibrations, if you want to find your A and phi, you don't care about your XP. You can directly plug in your X naught and V naught and get your A and phi, right? But then if you look at these force vibration, look at your slide number 4, you can find out that your A and phi, they're not only functions of your system parameters and initial conditions, they're also functions of X and theta, right? And remember that big X and theta, they're from steady state. So that means your A and phi, they're determined by system parameters, determined by initial conditions, and also determined by steady state response. So in other words, you have to calculate your steady state first, then you can calculate your A and phi. All right? So let's look at your steady state. So your steady state is big X times cosine omega t minus theta. So these minus signs giving me trouble all the time. So in the textbook, we use minus, and in all these slides, we use minus. But in my lecture note, but in my explanation, I use plus. Just pay attention to that. So if you choose to use all the equations here, then it's a minus in front of your theta. Okay. So all your X, big X amplitude and theta, they are functions of omega. They depend on the, they all depend on the excitation frequency. So if you check my MATLAB code, if you plot the big X, and if you check my lecture note, plot the theta, your theta will be something like this. Oops. And then your X will be something like this. So these two plot together because it's a function of frequency omega. So we call these frequency response. And we also, there is another fancy name for it, which is called Bode plot. So Bode plot is actually not a one plot, it's actually a pair of plots. It plots both the amplitude and phase. So there are two plots. All right, so what you do is for a given frequency, you calculate your X and theta. And then once your X theta is calculated, then together with your initial conditions, you can find your A and phi. And eventually your solution will be the summation of the two parts. So how can you find the equations? So remember, you go to slide number 4 and then use all the equations here. And pay attention. So these equations only works for F naught cosine omega t. Only works for these force excitation. And it only works for this system. So that is the solution for this particular ODE. If you have other ODEs like what we're going to learn today, then all these solutions won't apply. But for example, I give you a hint or give you like an additional option. So what if you have a psi function as your input? Can you find all these 4 equations? All right, so that's actually what I asked for in homework number 3. Make sure you understand that, because in the I'm still thinking about exam number 2. I might ask you to solve a harmonic force system. Perhaps on the right-hand side, you're going to have F naught sine omega t plus 1/4 of pi. what if you have excitation like this? What's the xt I should expect? Or if it's f1 sine omega 1 t plus a quarter pi plus f2 cosine omega 2t plus pi over 3, something like this. I'm going to give you a crazy harmonic excitation, but there's still harmonic excitation. Can you use ODE 45 or use analytical solvers to find the xt? So that's something I'm expecting from you. So hopefully you can solve. So try to solve homework number 3, and then let me know if you have any questions. So that's for lecture number 8. So any questions for these equations? So to practice what we learned today, I highly suggest you to solve homework 1 and homework 3. So I give you all the system parameters, initial conditions, and force harmonic excitation. Can you find the xt? So I already posted the solution online. All right. Let me see. What's next? So let's start our new lecture number 9. So here we're going to cover both base excitation and a rotating unbalance, but I think we don't have time to cover both today. I'm going to focus on base excitation only in this lecture. So before going into base excitation, we have to learn one very important concept, which is called transfer function. Okay, so what is a transfer function? So as I said previously, like for sensor design or actuator design, so I would say most of the case, we will focus on steady state. So if your excitation, the problem becomes if excitation or input is some kind of harmonic excitation, what is your steady state response? That means, can you find your XPT, the particular solution, which is a big X times cosine omega t minus theta, right? So that's actually a very common question in industry or in a future career. So you know that you already know your system, and you know your system is subject to a harmonic excitation. You want to know a steady state, how your solution look like. So previously, the way we find these XPT is trying to solve ODE, and then you plot the time domain response, and then you check long enough of time, make sure your transient state is completely die out, and then you pick that solution as your steady state solution. So that's going to be really, really time consuming. And then I don't think any of you really like solving ODEs. So here we're going to learn this transfer function method. So we don't have to solve ODEs anymore. We have better ways to find your steady state response. So your steady state response actually have two things: amplitude and theta, which is your phase, right? So these two things are to be determined. So then we have to make a couple of more assumptions. First, we assume you have linear systems. So transfer functions only works for linear systems. That's because only under linear systems the superposition principle can be applied. Right? And another assumption is we assume your system actually that's not assumption, is actually true. So initial conditions have no effect on steady state. So that means if your system, if your zeta is 0, then your x naught and v naught are all 0. If you have damping in your system, then your your initial position, initial velocity dies out, right? So for transfer function, because we're only interested in transient state. Oh, sorry, we're only interested in steady state. So we want to eliminate all the transient state or eliminate the effect of initial conditions. All right. So if your system satisfies all these three conditions, then we can use a so-called transfer function. A transfer function is usually represented by Bode plot. Then you have your amplitude, and then you have your phase. So you're going to need to find plot number 1 and plot number 2. So that's your transfer function. And then in order to simplify our discussion, you usually normalize your amplitude by the amplitude of your input. And then in that case, your transfer function is defined as output divided by input. So that means, so if you look at this, that means there is no unique way to define a transfer function. For example, if you have your mass, spring, damper system, your input is a force, and then your response is xt. If I ask you to find out the transfer function of this system, then you shouldn't be able to do it because I didn't tell you what is the input, what is the output. So you can, in this case, your input can be your force, and then your output can be anything. It can be your displacement. It can be k times x, which is the force in the spring. It can be c times x dot, which is the force inside of the dashpot. It can also be mx double dot minus. This is the inertial force of your mass. So you have the freedom to choose the output, but then how you choose your output determines which variable is of your interest. If you want to analyze the displacement, then you choose your displacement as output. In my previous lectures, I give you an example about someone jumping on the table. And in that problem, we're interested in the strength of your table legs, which is your K. So that's why we have to pick K times X as your output. All right. So that means before you calculate or before you want to derive the transfer function, you have to find your input. You have to find your output. Otherwise, you won't be able to do anything. All right. So once you identify your output and input, then you can use Laplace transform. So that's the original definition for Laplace transform. You don't have to understand that. It's really complicated. But I would like to give you an idea is if you have a first order time derivative, what you do is you put a single s. We call this s Laplace operator. You put a single s in front of your function. If you have second order derivative, you put a s squared in front of your Laplace, in front of your function. You can actually do, like going further, you have your nth order of time derivatives. You just put s to the nth order in front of your original equation. So for Laplace transform, the original format, if you check Wikipedia or Google, if you search Laplace transform, it always gives you some additional terms. So these additional terms so they are related to your initial conditions. So in later lectures, I'm going to teach you how to include these additional terms. But remember, there is a very interesting assumption at the beginning. We assume that the initial condition have no effect on your steady state. So that means if you just want to use Laplace transform to calculate transfer function, you can remove these additional terms. But that only works when you're trying to calculate transfer function. All right. So right now, since you only learned Laplace transform, then I don't expect any problems. But later you're going to learn the so-called inverse Laplace transform. Then the initial conditions becomes critical. So don't get confused. If it's for steady state, you can ignore initial conditions. If you want to find out the entire time domain response, or you want to solve an ODE, then initial conditions have to be selected. All right. So right now I mentioned steady state. I mentioned Laplace transform. So what's the connection between these two? I'm going to give an example here. So that's the system we learned last time. And I think I forgot one X here. So you have a force applied to the mass, and then the mass is connected to a dashpot and spring. And then in this case, we want to find out the transfer function of the system. And then let's assume that our output is xt, and then the input is ft. So that means we already know how much force we applied. The property of interest is we want to find out steady state response of xt. So that's something we don't know because we want to find out steady state response of xt. So that's why your output of your transfer function have to be xt. All right. So let's assume your ft is f naught cosine omega t. And then we know that at steady state, your response will be at big X cosine omega t plus theta. I'm using plus here because in MATLAB prefers plus. So let me use plus here. So that means your steady state is something like this. And then you just need to find out your phi, your amplitude, and your theta, right? Then how to find your big X and theta? So what we do is we're doing Laplace transform on both sides of the equation. What it does is if you have a function f(x), then you write it as fs. If you have df(x) dt, then it's f times fs. If you have a second order equation or second order time derivative, it's just s squared fs. You can actually expand these assumptions. If you have nth order time derivative of a function, then it becomes square. Oops. I should write it, these x should be replaced by t, because your x should be a time-dependent function. Your f should be a time-dependent function. All right? It's really simple, right? You just find all the time-dependent functions in the equation and then replace it by Laplace functions. So let's do these one by one. On the left-hand side, oh gosh, running out of space. Let me do it in here. So on the left-hand side, your ft, indeed, it is a time function, time-dependent function, but there's no time derivatives in it. So you just replace your small t, small f, by big F, and then t replaced by s. That's your left-hand side. On your right-hand side, you have three terms. You just do Laplace transform for each of them one by one. So the first one, you have x double dot. If you write your x double dot out, oops, let me see. Your x double dot is actually the second order derivative of your xt, right? So that's why your x double dot becomes s squared, and your x function becomes a big X, and then that's you replace your t by s. You just repeat this to omega n zeta, and x dot becomes single s times xs, and eventually you have x omega n squared xs. So this is from your velocity, this is from your acceleration, okay? So once you have this, then remember your transfer function is output divided by input. So that means your output is the displacement. Your input is the force. So you just need to find out the ratio between the output and input. What you do is you just move things around. You go back to this equation and then collect terms. You move the xs to the left-hand side. You're going to have 1 over s squared plus 2 omega zeta s plus omega n squared. So this equation in Laplace domain or in S domain is called your transfer function. So once you have your transfer function, then the next question is how to use this transfer function to find your amplitude, big X, and find out the theta. So the second step is replace S by omega J. So you replace all the S in the equation by omega times J, or by a complex number. So your X over F omega J. So it's no longer a function of S, it becomes a function of omega. Oops. Because J is a constant, so you have a function of omega. And then the numerator is still constant 1, but then denominator becomes omega n squared minus omega squared plus 2 omega n omega zeta j. So in this case, you convert the Laplace transfer function to a function of omega. And then this function is usually a complex number. So then what you do is you can get two plots, as I mentioned before. One is the amplitude plot. And then the other one is the phase plot. And then they're all functions of frequency. So we already know that your excitation is f naught over cosine omega t, or we already know that your small ft is f naught cosine omega t. So this amplitude here is actually equivalent to big X divided by f naught. The theta phase is still theta phase. So I can give you an example. If we know omega is 10 radii per second and your f naught is 20 Newton per kilogram, you already normalize that. If you find your x, big X, and you want to find your theta. So what you do is you go back to these body plot, and then you find out your omega equals to 10, where the omega equal to 10 is. And then whatever value here is your theta. And then whatever value here is x over f naught. And you know your f naught is 20. You just multiply that value by 20. You get your x, big X. Make sense? So that's how you, when you have ODE, you want to find the steady state response. That's how you do it following transfer function or following Laplace transform. You just replace time-dependent functions by S functions, and then you shift things around, make sure you put your output on top, input on the bottom, and then you find the transfer function. And you replace all the X, you replace all the S by omega j in your transfer function, and then you get a complex number or complex equation, and you plot this complex equation against your driving frequency omega. And then if you know your omega and your driving amplitude, then you can find your steady state response. So by doing so, you don't have to touch the ODE solution anymore. Everything happens in the frequency domain. Is it clear? Yeah, okay. So let me give you another example. Still using the same system, but here we want to look at the taper lag design. So we want to check steady state response of k times xt, right? Because we're more interested in what's the force experienced by k. That's the steady state we're interested in. If you're interested in these, then that means your output should be k xt, right? Your input is still the driving force, which means we need to find your transfer function. Your transfer function is going to be k xs divided by fs, right? Make sense? Because it's no longer x over f, because we're not interested in x. We're interested in k times x. We are interested in what's the force experienced by your spring. Because k is a constant, then you can put k in front and fs. We already know the second term, right? We just derived that. Your k equals to 1 over s squared plus 2 omega n zeta s plus omega n squared. All right, so that means if you want to calculate the amplitude of k times xt, and then you already know, so the omega and f naught are given. Then in order to calculate your amplitude of these force experienced by your spring, you just need to find out the amplitude of your transfer function times the amplitude of your force. And then the amplitude of the force is your small f naught. And then the amplitude for your transfer function, what you do is you replace omega, you replace s by omega j, and then calculate the norm of that complex number. And then multiply these two together, you get your steady state response of your spring force. If you want to write it out, it's extra k 1 over omega n squared minus omega squared plus 2 omega n omega zeta square, take a square root, and then times f naught. And remember that your f naught is big F naught divided by m, right? And then your k over m can be replaced by omega n squared. You have omega n squared over omega n squared minus omega squared plus 2 times your force amplitude. So eventually the spring force can be directly calculated from here. If you compare these equations from the equations we got in lecture number 8, they are actually identical. So my comment is, from these examples, hopefully you understand the point. So the first question, when you want to apply steady state, you want to apply transfer function method, the first question you should ask yourself is like, which physical parameter I'm really interested in? Am I interested in the force? Am I interested in the displacement? So if you want to analyze that, the steady state for that specific parameter, then you have to put that parameter in numerator of your transfer function. Anyway, we're gonna check. So right now is a spring mass damper attached to wall, and then you have a force driving it. So we're only tuning the output. We haven't touched the input yet. So we can actually try to use different inputs as well. So I'm going to give you more examples here. One typical example is called base excitation. So when you drive a car, you can assume this big mass is your car chassis, and then the bottom of this base is, or the base is your tire. So when your tire is hitting a really bumpy road, in this case, it's very special. When it's hitting a harmonic or sinusoidal road, you want to check if a passenger is sitting on top of these seats, then you want to make sure, you want to check, investigate how your passenger feels when it hits a bumpy road. So actually, that's why base excitation is very common in practice. So first of all, let's derive the equation of motion. We need to find your ODE first. So let's use Newton's method. We haven't touched Newton's method for a while, but here is relatively easier. So you have a big mass. The big mass is experiencing a displacement x. And then what forces are experienced by mass? You have your spring force, Fk. You have your damping force, your Fc. So your Fk is k times y minus x, right? So which means if your base moves more than your x, then your spring is generating a force pushing your mass upward. So that's why it's k times y minus x. Similarly, your Fc equals to c times y dot minus x dot. That means if your base moves faster than your top, your damper is going to push your mass upward. So according to Newton's second law, you have Fk plus Fc, which is going to drive your system upward. And then you can plug everything back and move things around. I'm going to skip that. You have x double dot, cx single dot. Oops, so many dots here. Plus kx equals to cy dot plus ky. So that's your system function, or system ODE, or equation of motion, a lot of names for it. All right, let's normalize it. Then you have x double dot plus 2 omega n zeta x dot plus omega n square x equals to 2 omega n zeta y dot plus omega n square y. So that's your normalized ODE. All right. So we want to analyze the system. Here I propose two examples here to analyze this system. The first one is called displacement transmissibility. I can give you an example. So for the first case, it's actually very common if you ever do an internship or worked as a research assistant in a lab. You're going to see this equipment, I believe, in 99% of the mechanical labs. You're going to see a big steel table. That's your tabletop. That's your floor. Okay, and then that's your legs. You're going to see most of the lab have a table like this. And then this table and those labs running experiments, that's equipment, on top of this tabletop. The reason why is we call this table as vibration isolation table. And some people from ECE, they want to call it like optical table because they want to put lasers and other like optical devices on top. So the function of this table is if somebody else is having a party in an engineering building and you still want to run the experiment, you don't want the vibration caused by the party interrupt your measurement. So in this case, your floor is vibrating YT. You want to minimize the displacement caused by the floor vibration. Make sense? So do you understand the problem description here? So you're running a very, very precise experiment. You want to mitigate the negative effect of any floor vibration. So what you do is you want to design such a table so that no matter how your floor vibrates, the vibration on your equipment will be minimized. Make sense?
So is this supposed to be, this particular situation is very much equivalent to the initial statement above, or the initial problem above with the base excitation?
Yes. So
Okay.
this problem is related to displacement transmissibility. I'm going to explain that. So you know your input, right? So your input is YT, right? Because we already know somebody is jumping on the floor. So that's your YT. And then your output is your XT, right? Because we want to minimize that thing. So that's why you have pick that parameter of interest as your output. So which means your transfer function is displacement, is output versus input, right? And then let's calculate how this look like. So let's go back to the original equation. Let's do Laplace transform. X double dot becomes S squared, X big XS. Velocity becomes XS times S plus omega n squared. X becomes XS. The same thing applies to Y. Your Y is also time dependent. You have 2 omega n psi ys times s plus omega n squared ys. We already know the transfer function of interest is x over y. So that means your x over y s, move things around, you're going to have s squared plus 2 omega n zeta s plus omega n squared over 2 omega n zeta s plus omega n squared. So that's your transfer function when your output is x, when your input is y. All right? So let's forget about the phase. To simplify our discussion, we assume that your yt is y naught times cosine omega t. And then at steady state, oops. Your xt, oops, therefore becomes big X cosine omega t plus the phase lag. We want to minimize amplitude, so that's why we only care about these big X. So big X only appears in the amplitude of your Bode plot. So that's why we want to find out X over y naught, right? X, the ratio of these two amplitudes equals to the magnitude of f over y omega j. How you get x over y omega j? You just replace the s in your transfer function by omega j. And then you're going to have this complex equation. Let's copy and paste. You have omega n, oops, omega n squared minus omega squared plus 2 omega n omega zeta j. On top, you have 2 omega n omega zeta j plus omega n squared. You already find these complex number. And then you want to, and then your ratio is the magnitude of this. You can use MATLAB to calculate it, or you can go back, refer to the equation I gave you during lecture 8. You just calculate the magnitude of your denominator. Oops. And then you calculate the amplitude of your numerator, denominator, and then you put them together. Then you have such a function. So in this way, if you look at your output amplitude here, so these amplitudes equals to a ratio times your y naught. Y naught is your excitation. And then you want to minimize your x amplitude in this case, right? We want to minimize impact of your base excitation. So first of all, how to design this table from that mathematical equation. So based on this equation, can you give me some hints? You want to minimize your big X. What you can do?
Make the ratio,
Yep.
Make it really small.
Yep. Actually, you can either minimize your ratio or minimize your y naught, right? So that means that's why in some of the labs, like for example, in geoscience lab, as far as I know, they're running some really high accuracy laser experiments at night or during the weekend when nobody's in the building. So in that case, your y naught is minimized. So if you have no control on y naught, like for example, you want to run experiments during work days, then you want to minimize your ratio. Then how this ratio look like? If you check my lecture 9 underlying examples, I actually give you a MATLAB code helping you to plot these ratios. So these is the images. So here, this is the images you're going to see. And then this is your ratio. Again, your transfer function has nothing to do with initial conditions, right? So that means your ratio has nothing to do with initial conditions. So it only depends on the system parameters. Your system parameters are K, M, C, and omega, right? So that's the only 4 things you have control. And then remember your K and M, K over M square root, that's your omega n. So in order to simplify our discussion, in this plot, we also normalize your frequency ratio. So your frequency ratio R equals to omega over omega n. And then we want your table works in the region where this ratio is really tiny. Let me draw a line here. This line, left or right. So first of all, do you want your table to work on the left-hand side of the curve or the right-hand side of the curve?
Right side.
Yep, correct. You want to minimize that ratio, right? If you look at the curve on the left-hand side, you actually have very minimal control of your system, right? So at the beginning, when your R is 0 or when your omega is 0, so that means you're giving your table a static push. So no matter how you design your system, this static push is going to be transferred to your target. So you have no control on low frequency components. And then at low frequency, there's another thing which is really severe. That's called resonance. This is called resonance. So that means if somebody is dancing on the floor in a specific frequency, that might actually give you a detrimental impact on your experiment. All right. So that's why you want to design your system such that your system always works on the right-hand side of this blue dashed line. How can that happen? And then if it works on the right-hand side, do you want high damping or low damping? Let's assume that we're already working on this right-hand side. So you want high or low? So if you look at the curve, it should be low damping, right? Because when zeta equals 0.7, it's actually above the curve when zeta equals 0.1. That's actually against our intuition. When you want to isolate a vibration, my intuition told me that you might want to increase the damping so it absorbs more energy. But actually, that's not the case. If you, in most of vibration tables, you don't see a lot of damping. All right. So the last question is, how can we make sure your system always works on the right-hand side? So that means in this case, you want your R greater than square root of 2, or omega over omega n is greater than square root of 2. So that means you want to reduce your omega n or increase your driving frequency, right? Most of the time, we won't have control on the driving frequency because that's the environmental impact. So it all depends on all the residents or passengers or like students in the building. So we have no control on your omega. So that's why we have to lower the resonance of your system. So remember that omega n equals to k over m. That means you want to decrease your k and then or increase your mass. So that's why, yeah, if it's not online teaching, hopefully I can show you the vibration table in my lab. So that table is actually pretty huge. So this tabletop is actually made of stainless steel. It's pretty heavy, perhaps a few hundred kilograms, half a ton or something. It's a huge mass floating on 4 pneumatic supports. So in practice, your spring support will be some pneumatic cylinders. And then your mass will be a stainless steel tabletop. So if it's pneumatic cylinders, then basically your tabletop is kind of like floating in the air. It's pretty soft. If you even even you touch your tabletop slightly, your tabletop is going to vibrate. And then the mass is huge. By doing so, you're decreasing your omega n. That means you're reducing the natural frequency of your system. That means you have a higher chance to operate on the right-hand side of the resonance. All right? So hopefully this example teaches you how to design your system using transfer function. Let me see. We still have about 9 minutes left. I'm going to give you an example, and hopefully you can have the discussion after class. So I'm expecting you to do similar discussions in your final project. Okay. So the same problem, same system, but then in this case we're not talking about vibration table. We're talking about cars. Let's assume there is a driver sitting on a chair, and then the chair is supported by a mount or a shock absorber, and then this is your tire. That's a very simplified. The total mass of these two systems is M and is C, and then the road is bumpy. So the road profile, Y, is Y naught times cosine omega t. And then usually the comfortness of a passenger is measured by acceleration. When you say I had a smooth drive, that usually means your acceleration during the trip is pretty small. So you want to minimize x double dot. In other words, your output is x double dot. Your input is your bumpy road, which is y. As I said, when you have systems, your x double dot is determined by a lot of things: initial conditions, mass, spring, damping, and then also how bumpy your road is, and why not. Okay, so we already know that initial conditions has nothing to do with your steady state. Can you tell me how you choose? And then let's assume that your y naught is given because we have no control on the road. So my question is, how do you design your M, C, and K so that your output acceleration is minimized? So that's the force transmissibility example. Same ODE, same system, but we're just looking at it in a different angle. All right. So I already posted the solution and MATLAB code on Blackboard. Make sure you check it out. And I might spend about 10 minutes discuss this MCK design next lecture. All right. Any questions for today's topics?
These notes are going to be uploaded to the Blackboard as well, right?
Yes, I'm going to post the lecture 8 note and these notes on Blackboard right now. All right. So if you don't have any questions, just keep an eye on the Blackboard. I think I'm going to post a few announcements today. And see you on Wednesday then.